Okay, good afternoon. My name is Giuseppe Di Pasquale. I am a PhD, industrial PhD candidate at Aerospace, of course in collaboration with the UC3M. And of course I'm going to be talking about my progress in the past year. So this is the outline of our presentation. So I'm going to spend a couple of words about Aerospace, even though Borja covered it. Some words about the program motivation, the goals of my PhD, the methodology, and of course I'm going to focus on the results. As Borja said, what we do as a company, as a startup, we provide a propulsion system that is, the strength of it is deeply modular. And we also provide the software, which is what I'm involved on and I'm going to focus on in this presentation. So the program motivation. So basically, as Borja said, Athena is a modular propulsion system, and it's based on the electrospray technology, which is basically into this emitter, and this emitter is coupled with a reservoir that allows to capillary feed basically the emitters, these electrospray thrusters. The reservoir it can vary in size, so you can tune the size of the reservoir to actually achieve modularity at that level. So combining these two components, it forms what we call a thruster head. If we combine thruster heads with a power processing unit, that's how we achieve a deeply modular propulsion system, which is something that is nowhere in the industry, so it's really a novelty. So to sum up, in principle, the propulsion system has several design variables, which are, as I said, the number of thruster heads that we can use, the size of each reservoir, and also we can set some points. We can set the voltage, of course, so it can change the operations of the system. So by setting all these variables, we can actually obtain a system, so a propulsion system, which has set certain physical characteristics in terms of mass and volume, of course, but also some specific performance, so in terms of thrust, ISP power, and the total impulse that we can deliver. So in principle, this is how we can achieve a tailored propulsion system for platforms that can be very variable. You can see some example here on the right of basically a 3-unit CubeSat with different configuration of power system, and you also see how the propulsion system adapts to higher power levels or demands in terms of mission and maneuvering. So in principle, what I described is what sort of like a hybrid problem, because we have both discrete and continuous variables. And also we want to give our customers the possibility of choosing what are the objectives that we want to optimize for what concern the development of the thruster. Additionally, the problem is strongly coupled with the orbital dynamics. And of course, when you have a low thrust propulsion system, you need to solve the optimal low thrust maneuvers, which is not a trivial problem. And finally, we also want to have high realism in our solutions, so we also can enforce complex constraints in the simulations, as for example, power-related constraints, battery-related constraints, pointing constraints, visibility, and so on. So this is the problem, and all of this converges basically in the goals of my PhD. This is the first goal, which was the development of a software for basically optimal guidance of low thrust maneuvers in LEO, even though we also want to extend it more broader, let's say, also to other orbits. And in particular, so defining an algorithm to design and optimize a modular thruster, but also we extended it to performing concurrent subsystem design, so not only focusing on the thruster, but also on other subsystems. And we're also extending it to constellation deployment and maintenance, because constellation is actually a very big topic right now, so we're tackling also this problem. And so all of this converged into 360, which is the tool, basically the workhorse for mission analysis at Aerospace. And I think this is actually a nice example of how, let's say, research converged directly into the industry, so a tool that is that we're using literally on a daily basis with customers. So this is the present, let's say, and of course I'm going to be working on improving the tool, but also looking at the future. The second goal of my PhD is also tackling the attitude problem of the attitude side of the problem. So developing control laws that can be coupled with the guidances that are obtained with the first goal, of course. because in fact the electrospray could actually be used potentially as an attitude control system, not only as an orbital control, so as a thruster. So this is the methodology that I've been following, was basically focusing on creating a framework. This framework is based on a high-fidelity propagator. So we have orbital and attitude dynamics, state-of-the-art kind of propagator with various perturbations, gravity, drag, basically the state-of-the-art of what you could find in a tool like GMAT or STK. We also have models of systems, various subsystems, so not only thrusters, but also, for example, other subsystems like the EPS, the ADCS. And of course, we also consider events because, as I said before, we want to have a tool that is highly realistic and produces solutions that that have a high degree of fidelity. This fidelity propagator is coupled with an algorithm, which is called the QL algorithm. It's actually very famous in the astrodynamics community, which is basically a predefined control law that allows to generate near optimal guidance flows very rapidly. It allows to target multiple elements, so we can do any kind of maneuver basically with this QL. And there is also some nice heritage from UC3M and from Professor Sankurvo. And all of this is basically coupled with a genetic algorithm, which is particular NSGA2, also very famous. And in principle, this is the core of it because it allows to solve these hybrid multi-objective optimization problems. And in fact, the strength of a genetic algorithm is its versatility. So we can basically solve a lot of problems, a lot of different problems. It's just a matter of setting up the problem in the right way, and then the genetic algorithm can deal with multiple variables, multiple constraints, multiple objectives. And of course, you don't require initial guess, and on the long run, you kind of end up in the global optima, typically. And we also have parallelization. We also use a lot of parallelization because, of course, the weakness of the genetic algorithms is the function. You need a lot of function evaluation. So parallelizing is a key in this case. So I'm going to jump into some examples. So this was an example of design of an antenna thruster. You can see on the right Pareto front, so the set of optimal solutions with regard to two objectives, in this case the propellant mass and the time of flight for a given maneuver. And what you can see is that you have many points. Each point represents a solution for the thruster, but also for the optimal maneuvers that you're performing. And actually, you can notice that all these points are the same power and the same actually configuration in terms of stacks. Thruster heads, but the maneuver is actually performed in a different way. So the customer, in principle, has the freedom of choosing the design of the thruster, but also the way they perform the maneuver, depending on the objectives that they have. Another example, this was it was an unconstrained problem, so it was certain sets of maneuver, actually. One of the objectives was the cumulative firing time, so with all the maneuvers, we wanted to minimize the time that we spend firing. And on the other objective was, in this case, the propulsion system mass. So we wanted to minimize the footprint of the propulsion system on the spacecraft. And what you can see here is, in this case, 3 different designs with different maneuvers and a minimum cumulative firing time of 1.8 months. In the moment we add constraints, in this case, for example, it was a battery limitation constraint. So we were also simulating the power system, so how the power is generated through the attitude and how the battery discharges, depending also on how you use the various equipment. What you can see is the modification of the Pareto front, how the minimum time goes from 1.8 to 2.3 months. And this is just an example of how we can inject complex constraints into the design. So this is another example, going more, adding one layer of complexity. Basically is, again, a design of Athena, of a thruster, modular thruster, but adding also other subsystems into the design variables. So in this particular case, we were tackling also, for example, the solar panel configuration. And you can see, in this case, also we had three objectives. So the time of flight, propellant mass, and the system mass, the total system mass, so the mass of the whole satellite. And you can see we obtained 3 families of solutions, more or less. It's a bit hard to read because it's a 3D Pareto front. But you can recognize clearly there are some solutions with body-mounted solar panels. some with single deployable and double deployable, and also different configurations of Athena. So another problem that I've been tackling, as I said before, is the constellation deployment. This is a huge problem right now in the field because everyone is doing constellation, of course. So what we've been tackling here is actually the deployment using onboard propulsion and exploiting the J2 harmonics. And we analyzed basically two methods. The sequential method in which the satellites are basically perform the same maneuver but with a certain delay, and this on the long run allows you, thanks to the G2 perturbation, to obtain this orbital plane spacing. So you subdivide the planes using onboard propulsion, as opposed, for example, to launching the satellites directly into the right orbital plane, which can be very costly. And the other method is this parallel method in which the satellites actually perform the maneuver concurrently, so at the same time, but they perform it with different magnitudes. So eventually you obtain the same subdivision, but in a different way. So what we found here is that if you don't have injection constraints, so if you're free to inject the satellites exactly where you want, that the parallel method is far more efficient than the sequential one, as you can see from this Pareto front, and the red one is the parallel. And this is because it seems like that the parallel method exploits better the natural dynamics because all the satellites perform the maneuver at the same time. But of course, there are also problems on that case because on a system standpoint, let's say, because for example, you might want to need to load the satellites with different propellant masses. So that could be a problem also to integration, and there could be other problems. We also analyzed several thrusters because, of course, we're performing this with different propulsion, with a propulsion system. So we wanted to see, for example, comparing the electrospray, so for example, Athena, against all effect thruster. And as you can see, the electrospray is very challenging, both in terms of maneuver duration against the all effect thruster, which is one of the systems with the highest thrust to power ratio. But at the same time, it can also compete with the FIP, that is one of the systems with the highest specific impulses, and you can see it here. So it's a very balanced solution that can compete with technologies that on paper have some things that are better, let's say. Another thing that we analyzed in this problem was the effective injection constraint, which is actually something that you could have if your launcher needs to drop you at a lower altitude, for example. And what we've seen is that the parallel method actually suffers greatly from limitations in terms of injection orbit. And in this case, if the injection orbit was lowered to 600 kilometers against 800 kilometers, which was the operational one, you see that the Pareto front of the sequential method dominates the parallel one now. So this is a big aspect. And also there is this plot that shows that basically, depending on injection altitude, one method could be more efficient than another one, at least in terms of deployment time. Another problem that we've been tackling is the variable specific impulse maneuvers. So the idea here is to use the system, the thruster, not at a fixed point during the operation, but varying your performance on the fly. So you can see here an example. You see how the specific impulse varies during the maneuver. The way we did this was, again, exploiting the same framework that I described before. In this case, the problem was posed as, in a way, the idea was to tie the performance, so the specific impulse, to the thrust effectivity. The thrust effectivity is a parameter, basically, that quantifies how effective is to fire at a given point of an orbit. So the idea, was to tie these two parameters through a parametric function and then optimize the parameters of this function. So by doing this, we obtain this Pareto front, the blue one, which is the one with variable ISP, against the red one, which is the one with constant ISP. And as you can see, we have, it's a bit better. It's not a lot of gain, but is about 10% for example, for the same time. Which maybe it's little, but consider that this kind of variation of ISP if you have the right technology, it kind of comes for free. So if you get a 10% almost for free, I think it's a good bargain. And these are the, let's say, the curves, the parametric curves obtained for different, in this case, maneuver duration. You see how the shape changes, the genetic algorithm found different a different solution depending, on, of course, on the objectives. And I'm going to conclude with the dissemination activities that I carried out. So I participated in the 5th Microproportion and CubeSat conference in September 2021, where I presented my progress at the time. Then in the European CubeSat Symposium, in which again it was a presentation, in this case focused on the concurrent aspect of the tool. Then I participated in the AIAA SciTech Forum 2022. This was, again, a presentation, and also there was a conference paper that was in the proceedings. I participated, okay, this was a system engineering workshop that was not really related to the PhD, but more on the company side. Participation to various seminars. And looking more at the future, well, we actually submitted last month a journal paper in Advances in Space Research that was about the constellation deployment strategies that I talked about before. Then I'm going to be participating in the IAC in September. The abstract was accepted, so we're working on the paper right now. And finally, we submitted the variable specific impulse methodology that I presented to the next AIAA SciTech, and we're waiting for a response. And that's it. Thank you.